Hey everybody, thanks for being here today. First Arrow meetup in San Francisco, so that's West Coast, first Arrow meetup in West Coast, I guess. So quickly, who am I? My name is Jacques. I am CTO and co-founder of Dremeo. I'm also an Apache member, involved with several Apache projects. I'm the VP of Apache Arrow, but also involved with Calcite and the incubator project at Apache. To start off, I just want to say thank you to, of course, Thumbtack, as well as the people from Dremeo and IBM as speakers, as well as Apache Foundation for being able to provide us a place to build something that's so important and built on a sort of a consensus approach to things. So I'm going to talk about two things. I'm going to talk about sort of Arrow in theory, and then I'm going to talk a little bit about sort of basic practice with Arrow. And then we'll have, after me, we're going to have a special guest speaker, Brian from IBM, who'll talk about the Arrow Spark integration. And then we'll follow that up with Sid, who's going to talk about some sort of heavy usage of how you can use Arrow in practice. So first, to just sort of get you on a primer here, Apache Arrow, think of it as a standard for columnar in-memory processing and transport. Okay, it's both processing and transport, which is an important thing that I'll hit on in a minute. It's really focused on analytics. There's other representations that are better for row-wise things or streaming things. Arrow is really focused on sort of large-scale reads and analytics. And in many cases, using Arrow and the techniques that are sort of around Arrow, you can get a substantial performance in your workloads, performance improvement in your workloads. You can think of it kind of as a common data layer. I think the goal with Arrow is to try to come up with a way to do a much better job of having a loosely coupled data ecosystem. So rather than having to think about things monolithically and having it be very expensive to move from one system to another, we want to make it easy so that you can pick the right system for the right use case and combine those things together. It's designed to be programming language agnostic, so it's an in-memory representation rather than a programming API or something like that, which is a little different than most things. And it's designed for both traditional sort of rows and columns, a relational model, as well as sort of arbitrarily complex data that you might see in sort of document databases or JSON files. And the most important thing about Arrow is it's an Apache Foundation project driven by a large group of people who all have their own sort of motivations around it, and so it's very consensus driven. Using Arrow is something that you can feel very safe about because you know that there's a lot of different people who are driving it together. So really goals, very simple. Well-documented, cross-language compatible, designed to take advantage of modern CPUs, embeddable in all sorts of things. So one of the important things to understand about Arrow is it's a library more than a system. And so it's designed to be incorporated into data applications you might be building or data infrastructure products that other people are building that you will benefit from, and designed to be very, very interoperable. It's a shredded, nested representation of data. Arrow is columnar in memory, kind of like Parquet or Orc or something like that is columnar on disk. A lot of the same kinds of ideas about how to make things efficient. Different approach, different sort of tactics to how to solve those things though. In memory, for example, we want to focus on random accessibility, whereas on disk, you really want to expect more streaming reads. And so that changes some of the representation. You also choose to use different types of compression in memory versus on disk because of your interaction being different. So want to maximize CPU throughput. The way that I kind of look at the world is that your first problem is pulling stuff off the disk. These days, people have such efficient formats on disk that they can pretty quickly pull stuff off of disk, and they have a lot of different spindles or SSDs driving information being pulled off of disk. Your next question is whether or not you can fit this stuff in memory. If you can't, then that's where your performance is going to be challenged. But then once you get that stuff into memory, the real issue is about CPU bottlenecks. And so how fast can we push things through the CPU? And that's where Arrow is really designed to sort of work very efficiently. It's also designed to allow you to do scatter-gather I/O when you're interacting between different systems, which can be very powerful. And so when you think about Arrow, it's kind of a chicken and egg a little bit, in that Arrow's goal is to try to make it so it's easier to move data between different systems. But the question about how you do that, we were thinking a lot about how to do this. And early on, there's a bunch of us involved in sort of brainstorming what Arrow, why does Arrow need to exist before it was even a project. And really it comes down to this sort of, you want systems to all speak the same language. And the way that happens today is that you have basically people come up with sort of these serialization formats, these transport formats, which are useful. And then what happens is each system that's producing data will go from an internal representation of data to this transport format, move the data across either the wire or a local socket or something like that to a second system. And then the second system will take the transport format and move it back to an internal representation. And so what happens is that you can have these sort of standardized transport formats, But what happens is you use huge amounts of CPU cycles moving from internal representation to transport format and then back again. And so when we thought about how do you solve for having a very efficient transport format, it turns out that you actually need to solve first for processing. You need to come up with something that's very efficient to process, because that allows people to use something internally and then be able to hand it to someone else in a transport format. And so if you can avoid the serialization and deserialization boundaries between systems, then that's a huge benefit. But the way you do that is to get people to adopt a format internally for processing purposes. And so as much as Arrow is designed to transport and move between different systems, its core is, hey, what is a very efficient processing format internal to a particular system, that then there's a benefit to adopting this for just the internal systems, not just for communication between systems. And so that's really these two parts, right? Is on the left-hand side, you can think about, hey, this is how we want to have better transport between systems. Let's avoid serialization. Let's come up with a way to push things on the network or on local or shared memory or whatever very efficiently. But in order to do that, let's come up with a representation that's columnar, that's very efficient for CPUs or GPUs to process. So it's kind of the two sort of sides of what Arrow is. So it's not just a transport format, and it's not just a processing format. It's really trying to bring those two things together. This is kind of an older chart here, but we've seen really good progress in terms of adoption of Arrow. So Arrow had its first release, I think, a year ago, plus or minus something like that, maybe a little more than a year ago. And we've seen towards the end of last year, we already were surpassing 100,000 downloads a month, which is great. And we've seen adoption by a large group of different people. So that's really what you want to see with an early open source project. In terms of its adoption success, it's tracking very well versus everything that you know and has become very common for today. So let's talk about Arrow basics. So Arrow has some sort of basic data types. You get scalar data types, booleans, different size integers, unsigned and signed, decimals, floating points. You got your sort of standard date, time, timestamps with different levels of precision. You've got your strings and your binaries. So that's sort of your standard scalar types that everybody might expect. And then you layer on top of that the ability to create structs, maps, and lists, which are kind of common things that everybody can understand if you're going to build a sort of hierarchical object. And then lastly, we have a union concept as well. So you can express things that are heterogeneous in nature. So for example, my first record has a column, which column A is an integer, and my second record is an array of strings. And so Arrow can also express those concepts, so you can pretty much express any data that you're interacting with Arrow. There's some more advanced types, like a tensor type and some other things as well, that are kind of early on in sort of the development. And so we're always looking at different ways. There's discussion, for example, of how do you express graphs inside of Arrow, and people are thinking about that as well. So there's more things happening, but these are sort of the core types right now. So when you think about Arrow, there's really this sort of, how do I communicate Arrow between systems? And so we basically think about it in terms of the first step between two systems is thinking about how do I negotiate schema. And so schema is like, hey, well, these are the fields, this is all the structure, here's the data types. We only need to communicate that once for a stream of Arrow records. And it's the sort of the logical description of things, right? After that, Arrow has one encoding that's allowed, which is a dictionary encoding in addition to a raw encoding. And so if it's a dictionary encoded set of information, then you get one or more dictionary batches which describe what is the nature of the dictionary data. And then lastly, you get what are record batches. And so the way that we at Dremeo use Arrow is we always try to keep record batches to 64,000 records or less. You can actually have larger ones if you're working inside of a system. It's not a limit of the specification, but it's useful if you're trying to do pipeline between systems. And generally speaking, when you go down to the leaves of a record or of a single record, you can't have more than 2 billion values because of the nature of how the spec is written. But usually that's not a problem for people. When you think about actually how it's represented, so Arrow, you got to get in your head, Arrow is a in-memory representation of data. And so what's specified is how the data is actually laid out in memory. It's like, okay, this is the first 4 bytes are this, the second 4 bytes are this, the third 4 bytes are this. And so it's designed columnar. And so basically for each data type, you have one or more arrays of bytes that are describing different parts of it. And so let's start with the middle column here. If we're saying this might be a 4-byte integer, which is age, expressing this data that's on the left-hand side, you're going to have 2 4-byte integers that are back-to-back in the data structure. And so what you can see is that the age data is in one chunk of memory, completely independent of the name data. Name, as a string, actually has 2 chunks of memory which are independent and can be interacted with independently. The first is what we call the offset structure, which describes the start and end point of each string value. And the second structure is the data structure, which actually has the individual value, the individual characters for the string. And so you can start to introduce these offset vectors into the data structures as data structures get more complex. And so the phones example here, where you have arrays of strings, introduces one additional offset vector, which is the list offset vector, describing what are the start and end points of individual sets of strings inside the underlying structure. And so you basically can use these types of techniques to build up arbitrarily complex data structures. And then when you're processing them, you can choose to only interact with portions of the memory depending on what the algorithm is that you're using. So for example, if you're trying to calculate how long the strings are, you can interact with the name offset vector, but you never have to interact with the values themselves. So there's a bunch of sort of benefits that you can do in terms of how you're processing. I think Sid will talk about that more in detail. When you think about the data, in this example, I actually simplified things a little bit. In Arrow, everything can be null or not null. And so there's actually one more piece of structure for all of these things, which is a validity vector, which describes whether or not for each individual record, whether or not the value is null or not null. And so when you actually lay these things out, this is the same data structure. When you actually lay these things out, you're going to see basically, as you're communicating, so we were talking about schema and dictionary up top, but then followed down below by the record batch. So these are record batches. One particular record batch is going to include initially what's called a data header. This is a very compact representation of how long each of the underlying buffers are that are associated with the data that's coming for this particular batch of records. That is followed by the 3 different chunks of memory associated with name, followed by the 2 different chunks of memory associated with the age, followed by the 4 chunks of memory associated with phone. Okay? Now, I showed these as being contiguous behind each other, and that's the requirement if you're going to go across the wire to somebody. But Arrow does support this concept of shared memory, of having a single data set that multiple processes can interact with. And in that case, it's not necessary that you actually put these things contiguously. So they could be all over memory space. As long as both systems interact with the same shared memory space, you can actually interact with these things without compacting them into a single spot. The other nice part about this is these data structures, you can actually line these things up and then just use scatter, gather, IO to send it across the wire. So in terms of components, I think I lost a slide here. Okay. I'm going to go into basically what are the components that make up Arrow. So the first thing is what we call the core libraries. And these are the different ways that you can interact with the representation. Okay? So if you want to create an Arrow data structure or you want to consume an Arrow data structure, then there's basically bindings for a bunch of different languages to do that. Java and C++ were the first that came along, but now there's Python, C, Ruby, JavaScript, and Rust, all available to interact with Arrow representations. Now, some of them don't support every data type today, but we're working hard to make sure that they do, and most of them support all the most common types that people are interacting with. And so if you're building an application today that is data related, especially if you're moving between multiple languages, one of the best ways to build that application is to use these tools to write Arrow memory and then share that memory across the applications. So one step on top of the core libraries is what I call the building blocks. That's an informal term that I call it. It's not what everybody calls it. And the 4 things that I think about here, 2 of them already exist. One is called Plasma. And Plasma is a single node in-memory store for Arrow representation of data that specifically allows you to have multiple processes sharing memory with interaction to that data. And so you can spin this up and you can load data into it, and then you can have different users who are potentially doing a Python application to grab some memory, interact with it, or a C application or whatever, grab some memory and interact with it, but several people can interact with the same memory so that you don't have to have multiple copies of your working data set. And so super interesting development there. Feather is another thing that's been built inside of Arrow. Feather is an ephemeral on-disk format. And so Arrow is really about in-memory stuff, and we don't recommend that the representation be used on disk for long-term purposes because it's not necessarily as efficient as other on-disk formats. It's also not designed to it's not optimal for on disk. That being said, if you have 2 different systems that you want to share data quickly and you don't yet have a way to do that over RPC or IPC, then one of the easiest things to do is simply use the disk as the intermediary. And so that's what Feather's about. It's about dropping the Arrow memory straight to disk. It's basically the exact same memory representation as in memory. Drop that to disk. You could then theoretically actually mmap that in another application and treat it like memory, and it's all in the same representation. So Feather's a very efficient way to move things between different applications, or if you're running out of memory and want to drop stuff to disk temporarily until you have enough memory again. The other 2 things that we're working on in the community, one is called Arrow RPC, and this is about trying to deliver on the concept of I'd be able to move data between any 2 systems. And so there's definitely lots of techniques to move data between systems today. but they're not necessarily optimized for this analytical workflow that Arrow is focused on. And so Arrow RPC is about having a standardized library that works with the core libraries in the different languages, allowing us to move data very quickly between two different systems. It's designed to, or it's going to be designed, or it's in the process of being designed to support both a RPC or an IPC approach, so I can use shared memory if I'm local. And then lastly, the other really important thing here is since we're dealing with large amounts of data, we're also very interested in supporting the concept of a parallel stream. So it's great if I'm interacting between two systems that are small, that a single stream is fine, but realistically with the data sets that everybody works with today, we really want to be able to parallelize the set of streams across many nodes so that two different systems can interact at massive scale. The other thing that people are working on is something we're calling Arrow kernels right now. That's the working name. And the concept here is that it's great to have a representation. The most common way that people adopt this, if they're trying to adopt it for their own application today, is because they're working in two different technologies that don't necessarily work well together, and they want to move data quickly between one and the other. Okay? The additional option that we see, this additional sort of opportunity we see, is that if we can give people very efficient ways to do a certain algorithm, let's say sort or dictionary encode something, then we can give them those tools and say, hey, if your data's an Arrow representation, we can do these very, very efficiently. And that's another way for people to start taking advantage of Arrow for a random use case that they might have. So on top of that, so you've got core libraries, building blocks, and then you've got Arrow integrations. And so there are several different projects. This is just a subset of the projects that have all integrated Arrow in one way or another. So one of the great things is Pandas has adopted it as an internal representation for lots of their processing and really trying to drive that direction. Spark now supports it, and that's what Brian's going to talk about, so I won't steal the thunder there. Drumeo is a project that we work on at Dremeo, which is built entirely on top of Arrow. The Parquet community, basically we figured out, Arrow, one of the things that we did is we built Arrow to also think about how on-disk representations existed and what is an efficient way to move between the two. And so the Parquet community has heavily adopted Arrow as a way to make it an efficient way to get data out of disk and into an in-memory representation. And so the C++ library built entirely on top of Arrow. And then the last thing I'll mention there is that the GPU Open Analytics Initiative, driven by NVIDIA and several other companies, also has adopted Arrow as the in-memory representation for things. And so that's really nice to hear because one, it's more support for the project, but it also sort of fits with what we approached it with, which is that the representation should be really efficient whether it's for CPU or GPU. So that's sort of a reinforcement of that point. So a couple more slides and then I'll hand it off here. So a couple of ways to think about Arrow. So we've worked with Arrow for several years now at Dremeo, and we've learned some lessons, some of them the hard way, of course. Sometimes happens that way. And so I just wanted to share a few of the things that we learned and how we kind of approach things. And so these are all in context to something we call Sebo, which is the engine that we have built around Arrow inside of the Dremeo product. And the Dremeo product's an open source project. You can go look at this code, and I have some links, I think, in some of this deck, so you can look at stuff. But it's built sort of entirely around the Arrow library. It's built on top of the JVM. So the three things I just kind of want to share in terms of sort of real world experiences. The first is memory management, the second vector sizing, and the third sort of how we approached RPC communication. So the first is memory management. And so one of the things that's different than sort of maybe a traditional database is that you've got these chunks of memory because you have all these independent pieces of memory for the different Arrow representations. And so what we do very extensively when we work with Arrow is we work hard on building hierarchical allocators and having a very clear concept of what is ownership of memory because we're constantly moving these vectors between different operations inside the system. And so what we did is we built something that's on top of Netty's JE malloc implementation that allows you to create a tree of allocators. And this is actually code that's inside of Arrow that we built through sort of a bunch of sort of trial and error. That allows you to sort of set two things. It lets you set a reservation for each of these different nodes inside this graph or this tree, and then additionally allow you to set limits around things. And so you can say, okay, I want to have a reservation of this operation of 1 megabyte of memory. I want to make sure it's no more than 10 megabytes of memory, and the allocator will help you sort of reinforce that to make sure that you're managing memory throughout the system. And when you think about Arrow, you're actually thinking about many individual chunks of memory, and so what we always interact with, at least in the Java library, it's called arrays in the C++. In Java, it's called vectors, but it's basically, when we say vector, we typically mean the collection of all of the buffers associated with a particular scalar data type, or a particular data type node, if you will. So something very important to focus on because as you start using Arrow, you'll find that because of the random accessibility and some of the other things, it can be a lot of memory. and obviously memory is scarce, and so being very aware of memory management is something important to think about when you're working with Arrow. This is kind of some stuff I talked about, but basically this concept of when we're working through, for example, an operator pipeline, we make sure we have a very clear concept of ownership across those things and how we can transfer between them. The second thing is that how big you create chunks of records is also kind of an interesting question. And so all of this is kind of based on some early work done by what's it called, the X100, MongoDB X100 papers, where they started talking about, hey, rather than doing the C-store stuff where I have entire chunks of columns in memory, I'm going to have sort of like row groups or smaller chunks of columns, columnar data in memory, but then I break it up by rows. And so that paper kind of identified this concept that like, hey, the optimal size of this might be 1 to 4,000 records or something like that. Maybe it was 1 to 16,000 in their particular example. And so we actually work on that same model, which is that we generally will start by targeting about 4,000 records at a time. And the reason is that you want to figure out a size of record set that is efficient for the overheads associated with the data structures. So if you picked one record, that wouldn't be very good because the overhead of the data structures would be very great and be very inefficient in sort of terms of representation. You also wouldn't get any of the benefits of sort of the columnarization, the vectorization. And so if you pick a very large chunk of data, then it takes a long time. It's very hard to pipeline it through systems. And it's just like if I imagine, for example, a batch of records that could be like 100 megabytes in size, when I'm going to push that across the wire, it's going to be very hard to sort of pipeline that through the system. And so basically what we did is we started realizing that depending on the width of the records, you're going to want to resize how many records you have in the set. And so we start with a 4,000, but we'll actually size it down as the record gets wider. So if you have 1,000 columns, you probably need something a lot less than 4,000 records because otherwise the overall data set will be too large. Now that means that you're going to pay a higher fixed cost for the overhead of the representations, but the flip side is it means you can still pipeline them through the system and not dealing with giant allocations, which can also cause fragmentation problems. And so that's something we kind of work through and people should watch out for is that as you get to wide batches, you want to sort of shrink down those things if you're trying to pipeline them through the system. The last thing to sort of hit on is that RPC communication. So we spent a lot of time, we used the structure that's identified in the Arrow spec to move data between systems, but worked very hard to build it so that we have a gathering right approach to things. And then we also have as close to possible a zero copy approach between systems. So yes, you're going to push it between two systems across the socket, but beyond that, try to minimize the number of copies to avoid problems. And so we worked through that a lot. And basically created this concept of a sidecar message. And so we have our own protocol today. It's open source, it's in our GitHub. But we have our own protocol today because we really wanted this ability to have the sidecar messages which hold the bulk of the data and are not processed through a normal RPC framework. One of the things we've been working with the gRPC community for some time is a way to try to express this in gRPC because that's a very nice library that has a lot of good support. And so probably the initial Arrow RPC will be built on top of gRPC, even though it may not always have zero copy. It may have it in some cases and not in other cases. So that's what we did with RPC. So that was my main slides. That's right, I had two more, I forgot. So one is that I've done enough talks to Arrow to realize that sometimes people just want to have it's not necessarily clear, it's kind of abstract. What is it, what isn't it? Okay, so what is it? It's a library or it's a set of libraries, that's what it is. It's a set of tools, it's a specification, it's a set of standards. It's really designed for being efficient in memory, and it's efficiently convertible to things like Parquet, where you're going to go columnar to columnar very, very fast. What is it not? Well, Arrow is not an installable system, right? Arrow does not replace X. Arrow is a new thing. It's trying to solve some problems that other systems solve pieces of, but it's a very sort of focused use case in terms of what Arrow is trying to do. And so you will not install Arrow. You may use Arrow in an application you're building, or you may use an application that has Arrow built into it. But those are going to be the two situations that you're most likely to use Arrow today. It's not an in-memory grid. And there's an exception here because Plasma is actually an in-memory single node solution, but don't confuse Arrow with sort of like an Ignite or a Tachyon because it's not about that. There may be people who build something like that on top of Arrow. So for example, someone like the Tachyon guys may say, hey, you know what, I want to support Arrow as an in-memory format in addition to the sort of disk format and the file system, in-memory file system approach, and they may support that, or one of the other sort of in-memory grids may support that, but Arrow is not really trying to drive towards that today. And the other thing is it's not designed for streaming or single record operations. It's designed for working with these large batches of records so that you can work through them very efficiently. And so if you're trying to solve an application where you're interacting with one record at a time and you want to move it through the system very quickly, Arrow is probably not the right thing. So that's kind of just sort of help with the what it is and what it isn't. I have to give a quick pitch. It'll be just 1 minute, which is what is Dremeo? So Dremeo is a startup. We're based in Mountain View. We were established in 2015. We launched the product in 2017. And we're really trying to build what we call a self-service data platform. It's a way to interact with data that's more easy to interact with. The narwhal's name is Gnarly, and I hope, Justin, we have stickers.
We have lots of stickers.
Okay, we have stickers. If you like Gnarly, you can get a sticker of Gnarly. And I think we even have stickers that don't even have our name on them. Do we have those? No?
Yes, but don't take any of them.
Okay.
Just the ones with the name.
Exactly. Kids like the narwhal. But anyway, our product is an Apache licensed product. It's built on top of Arrow. We use Arrow extensively. Everything that we do inside of our system is basically, we read data off disk, immediately turn it into Arrow, use it throughout the system, all the way out to the clients as Arrow. So we're big proponents of Arrow, and so that's what Dremeo is. So that's all I got. Questions for me before we hand it off to Brian?
So how does Arrow achieve fast processing?
How does Arrow achieve fast processing? So Arrow does not today in itself achieve fast processing. It is a representation which is optimal for fast processing, right? And so there are some algorithms implemented in Arrow. There's a bunch of work about implementing a bunch more algorithms in Arrow, but the representation as it's laid out, for example, and actually I think Sid's gonna hit a bunch of examples of this, but basically the representation is designed so that the types of operations you typically do against data are very efficient for how the CPUs like to interact with memory and cache and that kind of thing. Other questions? Back there?
So double-clicking on the thing that you mentioned about streaming and transactional use cases, if I have a bunch of records in memory in Arrow representation, can I change their values? Like, can I update those records in memory?
The libraries that are built for Arrow, think of Arrow as immutable. Since it's a specification, as long as you're managing the locking, you can. Right? Now there are some complexities to that. And so the example might be, is I have a bunch of strings that are sitting next to each other, okay? And the strings are all different sizes. If I want to go in and change one of the strings, it's going to be hard for me because I may not have enough space or I may have too much space to replace the string, right? And so there's no extra space and there's not a bunch of pointers. And so that can be kind of a challenge. But as long as you're controlling the locking, and we actually do this. Sometimes we will actually update the representation, but we never do that sort of where we're trying to communicate or share with someone else.
So fixed length values are okay, but variable length values are going to cause a problem. That's what it is.
Yeah, that's right.
And there is no support in the Arrow libraries themselves to handle this.
That's correct.